So the last time we were talking about expected values, or which were operations on single random variables. Okay, and expected values are other words we use for them, average values or the mean values or the first moment, and in some sense they are the weighted center, if you will, of a distribution or of a random variable. So when we say get the random variable, we would expect the random variable to be over here. So that's the average value that the random variable can take, right? One of the things we said is that the average value is not necessarily the mode of the distribution. So that's one of the confusions that students have, which is the average value is not where the probability is maximum, right? So that's not defined as the average value. That's actually something called the mode, right? The expected value is rather the average. You just, on the number line, you take the weighted average by the probabilities or the PDFs, and then sum everything up, right? So those are the expected values. The definition for the expected value, as you can see here, is in the case of a continuous random variable is here, right? So this indicates this is weighted, right? So weighted by what? Weighted by the PDF in this case. And for the discrete random variable, this is a definition where the weighting is not by the density per se, but the probability mass function. Okay, so these are the average values we did. We looked at this. We did not solve this per se, but I'm sure you would have done it. So this is by parts. So the average value, the expected value of an exponential random variable is this parameter B that we've actually seen before in distributions. Other than this, just वहाँ पे सारा एक parameter में इस्तेमाल करे थे. That was actually the mean value or the average value of an exponential random variable, right? So then we were doing this example for the Poisson random variable, and I said I'm going to do this again, so let's do that, right? So this is a discrete random variable. So for the computing the average value or the expected value, I am going to have to apply the definition, which goes something like this: that the expected value of x, this is defined as k times p x of k, right? So where k goes from minus infinity to plus infinity. However, I know that this random variable is defined only for non-negative values of k, right? So in other words, I could therefore have the summation go from where to where? Go from k equals 0 all the way up to infinity times k, and the PMF is alpha raised to power k e raised to power minus alpha divided by k factorial, right? Which is the same as if I start the summation from k equals 1 to infinity, right? Times k alpha raised to power k e raised to power minus alpha divided by k factorial. So why can I start this from k equals 1 and not from 0? I mean, the 0 term doesn't matter. Why not? Ji Ghazi, why does the 0 term not matter?
Because it's multiplied by k is equal to 0.
So it's multiplied by 0. So term is 0, doesn't really make a difference, right? So what do I do next? I make a change of variables, and the change of variables that I make is right. So another thing is that this k goes away, and I have this as okay. So I have this as k minus 1 factorial, right? So the k in the numerator cancels with the k in the denominator. So I have k minus 1 factorial. And then I'm going to make a change of variables, which is, let me choose a variable m, replace a variable m equals k minus 1. And because of this, what I have here is, this is m factorial. This is alpha raised to power m plus 1. This is e raised to power minus alpha. And this goes from 0 to infinity. And the reason is because when k equals 1, m equals 0. When k equals infinity, m equals infinity, right? So this is the summation, right? So this is equal to alpha times e raised to power minus alpha. And inside the summation, I have m equals 0 to infinity alpha raised to power m divided by m factorial, and then we know that because of Taylor's expansion, right? This term here really is e raised to power alpha, right? And therefore, what my conclusion is that the expected value of x is actually alpha, right? So the parameter alpha that we were looking at, for example, in the optical communication problem, उसमें एक parameter था, we said the number of photons that you receive or the number of electrons that you measure is Poisson distributed with the parameter alpha. That was actually the mean, the average number of electrons that you could expect to come out of the photodetector. Okay, so this is our conclusion, right? All right, any questions here? So as promised, this is the example done again. G. Josefa.
So if you had to differentiate the average value and the mode in distributions like this, then how would you do it, like in words? How would you describe that?
You see, for a आप exponential random variable को देख लें, right? Exponential random variable का mode क्या है? Right, so let me plot it here. So exponential random variables is f x of x equals 1 upon b e raised to power minus x upon b u of x, right? If I sketch it out, what does it look like? If I sketch it out as a function of x, the PDF is 0 here, then goes up, and then exponentially decays, right? The mode is कहाँ पे है?
0.
0 पे, right? So that's the mode. That's the, in terms of the probabilities, if you were to find the probabilities, right, in a very infinitesimally small region, that probability is going to be maximum around 0, right? And that can be an interval of very, very small length, or finite length. Okay? And that probability is maximum around 0. But that is not the average value. Why? Because the probability here is, even though this goes down, there's a significant mass here as well, right? Which is the area, right? जिसकी वजह से the average is shifted to the right. Right?
Okay, sir.
So the average value is somewhere going to be around here. Okay? I can give you another example, which is that of a Bernoulli random variable. Bernoulli random variable में PMF क्या होती है? So this is the example of a Bernoulli random variable. Let's say there's a Bernoulli random variable which can take on values between +1 and -1 and is equally likely. तो उसकी PMF क्या होगी? PMF होगी, there's a -1 and there's a +1. The probability here is half, and the probability here is half. What is the average value?
The average is going to be 0.
Average is 0, right? So actually the random variable actually never takes on the value 0, yet its average value is 0.
Okay, sir.
Okay? So in some sense, the average value is in some sense a center, right? It's a weighted center, if you will.
Okay.
Okay? Right. I mean, there are linkages with it. अगर आप वो center of gravity और इस तरह की चीजों से के साथ link बनाना चाहें तो बना सकते हैं आराम से. Right? That would require some thought, but you can make those establish those links. Okay.
Okay, sir.
All right. Achari, any more questions? By the way, a Gaussian random variable or a Gaussian distribution is one of those distributions in which the mode is exactly the same as the mean. ठीक है, जहाँ पे मैक्सिमम होता है पीडीएफ वहाँ पे ही मीन भी लाई करता है. That's Gaussian, and there could be other distributions like that. जी मुआज,
क्लैरिफिकेशन चाहिए थी कि मोड को डिफाइन कैसे कर रहे हैं हम?
Mode is defined as as the point at which the probability is maximum. Either the probability or the density is maximum. Okay, that's defined as a mode. Okay. Okay. Achari, if there are no questions, I'm going to move ahead to expected values of functions of random variables, right? So what I mean by a function of random variables is that you have a random variable x and you input that random variable into a function and you output another random variable, right? The output that you get is another random variable. So in other words, y in this case is a function of the random variable x. And what you're interested in is that if you're given the distribution on x, or you're given the random behavior of what x is, you are required to find, or you're interested in finding the average value or the expected value of the output y, right? Now, why will this something like this be important? There could be many reasons, but practically speaking, let's say you have a so you have a rectifier. Let's say you have a full wave rectifier. Okay, and so that's a box, right? And for this box, there's an input x, but that input x is random, and you don't know what it is. You know what the distribution for that input is, and the output is y, right? So what is the relationship, by the way, between y and x? Can anybody tell me if it's a full wave rectifier?
Absolute of x.
Absolute of x. So right, this is y equals absolute of x. ठीक है? तो आपकी एक इनपुट है, एक आउटपुट आ रही है, और आउटपुट जो है जस्ट द एब्सोल्यूट वैल्यू ऑफ x, which is the output of a full wave rectifier. And what you're interested in is if the input has a certain density or has certain distribution, what is the average value that you could expect at the output? ठीक है? And there could be many other examples. So let's say p equals I squared r, right? So you would say given density of the current, so the current is a random variable, right? What is the average power? Or what is the average power that you could expect, which is dissipated from this resistor? Okay. So these are the kinds of questions that you could ask, and what we're doing in this section would give you those the answers to those questions, right? Half wave rectifier hai, ya koi bhi aur function hai, right? So there's a current input, and you're interested in finding the energy or the power, and so on and so forth. Okay. So how do you compute this? So if y equals g of x, so let me go back and say, okay, if y equals g of x, expected value of y is defined as expected value of, because y is a function of x, and in particular a function g of x, and this is defined as g of x fx of x dx, right? So in some sense, this is actually a generalization of the expected value that we've done already. How? Because if g of x equals x, so that function is nothing but the input equals the output, this actually reduces to the expected value that we've done already, right? So this is just a generalization, right? And this is how you can compute through this definition the average value of a function of a random variable, or the expected value of a function of random variables, right? And this, by the way, this is applicable for a continuous random variable, right? What about the discrete random variable? Discrete random variable ke liye, this is going to be just the integral is going to be replaced with a summation, right? So where this is k, and this is x k p x x sub k, right? And this is for a discrete random variable, right? So for a discrete random variable, you're just working with PMFs. For continuous random variables, you're working with densities, right? Okay. Sorry, I've done something. So this is g of xk. So this is g of xk. And if y equals x, so this just is equal to xk. G Isha, go ahead.
Sir, there's just a little clarity that I wanted when we talk about a variable being like, it would seem very basic when I begin the question, but there's something else towards the end of it. Okay, when we say that x is a random variable, we are saying that x is random with respect to something.
Yeah.
Could be time or space. So when we're saying that y is a function of x, we're actually saying that x was random with respect to either time or space. And now y is random with respect to whatever x was random.
So Isha, so first off, I mean, it does not have to be time or space. It could be anything.
Could be anything. I just chose any of the two so that I could actually relate, because x won't be random with respect to y because y is a function of x.
Yeah, of course not. But y would
So
still be
exactly.
random. I mean, when you say
Yeah, why would it be random? But
Yeah.
then is it that we're actually just saying that it would be a set of parametric equations that x is random with respect to something and y would also definitely be random with respect to that something which x was random
Yeah, of course.
because of. So
So question क्या है?
so then sir question फिर ये है कि why can't we directly just model y to be random with that very thing, just say x
So
be random tha.
that's what we're gonna do afterwards. So given the PDF on X, you can find the PDF on Y. Or given the PMF on X, you can find the PMF on Y. And some of that you would have done or you would be doing in the homework as well. जिसमें कुछ ना कुछ जो है mapping of events है. Discrete के लिए चीज़ें आसान है. Continuous के लिए there's some slightly involved things that we would have to see, and we might be doing this in this lecture or maybe the next. ठीक है?
Okay, thank you.
All right. Okay. So let's do a quick example here. Any other questions? Right. So this is the simplest function that you can think of. This is an affine function. So y is an affine function of x, right? So small a and b, small b are not random, right? So they are deterministic, some constants, right? So what is random is capital X, and through that you obtain randomness in capital Y, right? So through that you obtain randomness in capital Y, and you're interested in finding the expected value of the output Y, right? So I'd say this the expected value of Y, which is mu Y. This is expected value of the function. So this is ax plus b. And I just apply the definition. The definition is what? This is a small x plus b times fx of x dx. So I am assuming implicitly here that the random variable is continuous, but the definitions extend easily to discrete random variables as well. Okay, so you just have to replace the integral with the summation, nothing else. Okay, so because integral is a linear operator, what can I say? Because the integral is a linear operator, I can say that this is equal to, a can come out of the integral, and then I have integral here. This is x fx of x dx plus minus infinity to infinity b fx of x dx. What is this equal to? What about the first term? What do you see in the first term? Asif, what is the first term equal to?
Sir, a into expected value of x.
Good, right? So this is a times expected value of x. And what about the second term?
So it might be 0.
Might be 0. Why?
सर ये मेरे ख्याल से b कांस्टेंट है तो इसकी एक्सपेक्टेड वैल्यू 0 आएगी.
Okay, so b is a constant, right? So you're correct. B is a constant, so B can come out of the integral, right? So B can come out of the integral. Now what do you see in the integral here? So the integral is just an integral of the PDF. And as Ghazi
PDF.
raises his finger there, the answer is 1. Okay, so the area under the curve of a PDF is 1, right? So the expected value of a constant actually, Asaf, is not 0, but the constant itself. Okay, so therefore, this is A times expected value of X plus B. And so expected value of A times X plus B is equal to this. Okay, so we see that there's some sense of linearity involved here with the expectation, right? So what I've actually seen is expectation can, so what I've seen is expectation is linear, right? It can go inside the, so inside the summations, and the constant can come out. That's what a linear operator is, right? Right? And I can generalize this quite a bit. And in fact, so so it's easy to show that if g of x is actually of this form, is a summation, okay? And this is a sub k, where k is some integer, you're summing over some integers, okay? Times g k of x, then expected value of g of x can easily be shown to be, this is expected value of summation k ak g of xk. So this is summation can come out a sub k g of expected value of g of xk. So this is g k and there's a k here. Right, so you can go ahead and try to show this yourself. This is very easy. It's just an implication of the fact that there's an integral involved when you're computing expectations, or integral is a linear operator, right? So if there's a summation inside the integral, the integral can come out of the summation, and you apply the integral first and summation afterwards, right? And that's what is meant by a linear operator, right? So essentially what this means is, okay, so this is that expectation is indeed a linear operator. What that means is, okay, scalars can come out and expectation can go inside summations. In other words, the summations and the expectations can be interchanged. Okay, so that is what is meant by expectation as a linear operator. Okay, any questions here? So I'm going to give some quick definitions. Moments is something that you may have studied already. Studied, yes or no? Ghazi, you know what a moment is? The nth moment.
I don't remember exactly. I think like x की powers होती हैं,
Yeah.
x square, x square.
Right, so the nth moment of a random variable x is defined as expected value of x raised to power n. So that's the nth moment. And of course, the definition from here would be that x raised to power n, and this is fx of x dx. This is, of course, for continuous random variables. और discrete random variables के लिए क्या होगा? So this is k x k raised to power n p x of x k. Right, so you just replace the integral with the summation, summation with the integral, and integral with the summation. Okay. Right. Acha. So tell me something. What about the 0th moment? What would that be? I mean, can you say something about the 0th moment of a random variable? What will that be equal to? Is this Mohsin? So this is expected value.
Sir, 1.
Right. So this is just 1. Right, because x raised by 0 is a constant. Right. So constant PDF. Yeah. So area under the PDF is 1, and therefore the expected value of a constant is that constant itself, and then constant here is 1. So therefore the 0th moment is 1 as well. Right. What about the first moment? This is the mean, right? So, and that is why, if you recall, when we said, KG, we're going to talk about the expectation of the mean value, one of the names we had for the mean or the expected value was the first moment as well, right? So the moment is really a generalization, right? And the first moment is actually the mean value of a random variable, right? What about the second moment? And this is n equals 2. This is the, so we say this is the mean squared value. And in some sense, this captures the energy in the random variable. कितना strong है random variable, उसमें कितनी power है, कितनी energy है उसके अंदर, right? So the second moment captures that, right? If the random variable takes on values which are small, so the second moment would expect to, on average, so we'd expect the second moment to be small, and if the amplitudes are larger on average, so we'd expect the second moment to be higher. Okay? So the second moment somehow, in some sense, captures the energy in a random variable. Okay. So let's do some examples here. And let's start out with the very, very simple example, which is a uniform random variable. And it's a continuous uniform random variable. So fx of x is 1 upon a when 0 is less than equal to x is less than a and is 0 otherwise. Right? So what is the first moment? First moment is nothing but expected value of x, which is the mean. I mean, even without computing this, you should be able to guess what it is. Right? So this is the definition. Right? So this becomes 1 upon a and 0 to a, and this is x dx. Right? So this is x squared by 2 0 to a. And what you get here is therefore a by 2. Right? So the center, actually the little center is the mean value of a uniform random variable as well. Right? So that's the first moment. What about the second moment? Or let's directly do the nth moment, right? So let's skip something. What about the nth moment? And that would be expected value of x raised to power n, right? I just apply the definition. So this is 1 upon a, and this is integral from 0 to a, and this is x raised to power n dx, right? So this is 1 upon a, x raised to power n plus 1 divided by n plus 1, and this is from 0, a to 0, okay? And therefore this is a raised to power n divided by n plus 1. So I've skipped a small step here. Okay? And therefore from this I conclude that the second moment is going to be what? Second moment kya hoga?
A square over 3.
A squared over 3. Okay? And from this you can compute any nth moment of this uniform random variable. Okay? Now, so you can go ahead and I'm not going to do this example here. I'm not sure if this is in the textbook. Maybe or maybe not. So compute the first and second moment of a binomial random variable, right? So for that you would have to use some summation, some binomial theorem, some expansion. It might be a little bit tedious, but you can go ahead and compute that the area or the mean of a binomial random variable turns out to be n times p, and that comes about from some tedious calculations, and which you should go ahead and try when you go home. Okay, you're already at home when you're done from the class, right? Achari. Then there's something called the central moment. Central moments क्या होते हैं? So central moments, just as the name imply, compute the moment around a center, right? So if there's a certain bias to a random variable, that bias is actually removed before you compute the central moment, right? And that center is really the mean, right? So you compute the moment around the mean, right? And the definition of the nth central moment, so the nth central moment is defined as the expected value of x minus mu x raised to power n, right? And you can replace this with an integral or the summation for the continuous random variable or for the discrete random variable. Okay. So what about the zeroth central moment? What do you think that should be? This is equal to what?
Say 1.
This is equal to 1. Good. Right. What about the first central moment? First central moment क्या होगा जी? Abdullah?
Yes, sir.
What would be the first central moment? If I plug in n equals 1 here, what do I get?
Sir, expected value of x minus mu x.
So I get expected value of x minus mu x, right? What is this equal to?
Sir, I'm not sure about that.
Okay, so just a while ago we said that expectation is a linear operator, right? So expectation can go inside. So this expected value of x minus the expected value of a constant is that constant itself. So this is 0. Okay, so the first central moment doesn't really mean anything. It's just always going to be equal to 0, right? The most important central moment which is used most often, is a second central moment. So much so that we have a special notation for that, which is sigma. And that is defined as expected value of x minus mu x whole squared. And this is called the what? ये क्या होती है?
Variance.
That's called the variance. Okay. So the variance is actually the second central moment, right? So it captures the energy in the random variable from which the bias has been subtracted, right? So it actually then therefore computes how much is the spread or the randomness in the random variable around the mean, right? Around the mean. Okay. So you're saying if I stand at the mean, I want to see कि मेरा जो signal है, मेरा जो random variable है, how much does it deviate from this mean, right? That in essence is captured in something called the variance, right? Which is a central second moment, right? It captures the energy, if you will, of spread around the center, which is around the mean. Okay? And this is related to the second moment, non-central moment. And as we're going to see. Ji Mohsen?
सर ये moment around the mean का concept को थोड़ा सा explain कर सकते हैं?
So you see, I mean, I can say that x minus mu x is another random variable, right? So if x minus mu x is another random variable, the central second moment is the second moment of that new random variable. And that new random variable is actually a random variable which is of zero mean. X minus mu x ka mean kya hai? That's zero. ठीक है? So x minus mu x is another random variable which on average lies at zero. On average lies at zero. और अब इस new random variable की आप energy देख रहे हैं. And that's called centralization, right? So you expect that, for example, you'd say कि class का mean जो है वो 80 है, right? And if I ask you to compute the second moment of the scores, right, that's going to turn out to be a large number, right? Because what you're essentially going to be doing is you'll be taking up each score, you're going to squaring them up, and then you're finding the average value of that score. And that score squared is going to turn out to be quite high. Okay? So for example, if everybody gets a 90, right? Each and every one of the students gets a 90. Okay? The second moment of this random variable is 8,100. Okay? Right? That's the second moment. But what about the central second moment? Central second moment when you say, let me just compute the mean first. The mean of the score is 90, right? And then I say, is mean ke around kitni deviation hai? And that deviation is none. There's no deviation there, right? So even though the second moment of this random variable is 8,100, the central second moment is zero, because the second central moment sees ke mean ke around kitni spread hai, uske around kitni energy spread hai. And that energy spread around the mean is zero in this case. Okay? So that's what the centralization does. You get it, Mohsen?
Yes, sir.
Right? That's what the centralization does. And then there's this relationship between the second moment and the central second moment, which we can just look at this expression here, which is on your screens, and try to expand this and evaluate what that relationship should be. So if I expand this slightly, and I see that this is expected value. So if x minus mu x whole squared is expanded into x squared plus mu x squared minus 2 times mu x times x, right? And from here, I just use the linearity of the expectation operator to conclude that this is expected value of x squared plus expected value of mu x squared minus 2 times, so let me do this. So minus expected value of 2 times mu x times x, right? So the expectation is a linear operator, so that means this has go inside the summation, right? And moreover, since this is a linear operator, the constants can come out, right? So this is expected value of x squared. What is the expected value of mu x squared? G Mohsin.
Mu x squared ही होगी.
Mu x squared yoga, because that's a constant, right? So the constant, the mean value of a constant is a constant, right? So this is mu x squared. And what about this term here? So 2 times mu x is also a constant, right? And this is expected value of x, right? So that constant comes out of the expectation, and I see that this therefore is expected value of x squared plus mu x squared minus 2 times mu x squared, right? And from here I can derive this or conclude that the expected value sigma squared is expected value of x squared minus mu x squared. Okay, so what this really says is that the central second moment is equal to the non-central second moment minus the mean squared, right? So this gives a relationship between the central second moment and the second moment. All right. Okay. So in other words, this is the second central moment is equal to non-central second moment minus the mean squared. Okay. So if you know one, you can always derive the other, right? Very, very quickly. If you know the mean and you know one of the other two. Okay. Now there are the third second moment, there are names for that. I'll just say out loud. I'm not going to write them in the notes. The third central moment is called the skewness, right? And the fourth central moment is called the kurtosis, right? You can find these names in the textbook. Skewness and kurtosis. Okay. So third is skewness and the fourth is kurtosis, right? I doubt if we're going to ever use them in any one of the problems in this course. Okay. So most important is the second central moment, right? Which is the variance, right? So let's do some examples, or one example. Okay, so you have a uniform random variable once again. So it's a uniform random variable. And that uniform random variable has a PDF equals to 1 upon A. So actually, let me, 1 upon A, 0 is less than equal to X is less than A and is 0 otherwise. Okay. Right. So we are required. So we evaluated the mean to be equal to A by 2. And we had already evaluated the second moment to be equal to A squared by 3. And from here, if I were to ask you what the variance is of this uniform random variable, I could compute the integral, and that's something maybe we can do afterward this. But since I know the second moment, and since I know the mean, I know that this is equal to expected value of x squared minus mu x squared. So this is A squared by 3 minus A squared by 4, and this is A squared by 12. Right, and if you wish, you can verify that this is true. Another way is to compute sigma directly from its definition. What is that definition? The definition is I'm going to integrate from 0 to a by 2, oh sorry, 0 to a. The PDF is 1 upon a. And what do I integrate? This is x minus the mean. The mean is a by 2. How do I solve this integral very, very quickly? Not so quickly would be that if you expand the squared out, right? And you get 3 terms, तीनों terms का अलग-अलग compute करें. I am going to do this with a simple change of variables, right? So this is 1 upon a, and then I'm going to say this is x dx from minus a by 2 to plus a by 2, right? All I've done is made a simple change of variables. Okay, so it's y equals x minus a by 2, right? And just replace that. So let's not do it. So this is y times dy, so that everything becomes symmetric. ठीक है, गाजी परेशान लग रहे हैं?
सर ये ऑड फंक्शन नहीं है जिसकी लिमिट्स
ऑड फंक्शन नहीं है,
0 हो गया.
Oh, okay.
y एक odd function.
No, so y is an odd function. Okay, all right. Y is an odd function. That's fine, right? So you could do this कि जी इसको 2 times कर दें और 0 to a by 2 कर दें. That's fine. You can do that. ठीक है? But I'd rather do this directly. So this is 1 upon a. This is y squared by 2, and this is a by 2 minus a by 2. Okay. So Ghazi, I like your idea. So this is 0, okay, and then this goes away, right? Because it's an odd function. Okay. All right. So, and therefore this is a squared by 4. So I've done something wrong here. Sorry. यार ये तो 0 आता है. So it's actually y squared.
That's what I was saying.
Odd function. Sorry, sir. This is y squared, and this is an even function, so you can multiply by 2. Okay. Okay. My apologies. Right. So this is 1 upon a, and this is y cube by 3, right? And this is from minus a by 2 to plus a by 2, and now you can multiply by 2 if you want to, right? And just take this limit from 0 to a by 2, right? So this is 1 upon a, and this is a cube upon 3 times 4, right? And then that cancels out, or 2 cancel ho gaya, and this is a squared by 12. You can go ahead and verify that this is actually true. ठीक है? All right. Any questions here?
सर अगर हमारा मीन जो है वो 0 है तो इसका मतलब है कि जो रैंडम वेरिएबल है वो फेयर है?
Not necessarily. Fair is a term which is not very strictly defined.
अच्छा.
Right? So if a random variable is 0, has 0 mean, all we say is it's a 0 mean random variable. And if it is a 0 mean random variable, that means the second moment and the central second moment is going to be the same.
सही.
Okay? So that's something I can say for sure, that the second moment and the central second moment is going to be the same for a 0 mean random variable. Actually, if it's a 0 mean random variable, all of the central moments are going to be the same as the moments, right? Because the mean is 0, so central का कोई मकसद नजर नहीं आता.
ठीक है सर.
ठीक है? All right. Any questions here before we move on? All right. So now we have something called the conditional expected values. And so the expected value conditioned on some event A. So this is expected value of a random variable. The definition for that is that expected value of x given A. So this is the notation, and this is defined as integral from -infinity to infinity. Any ideas? क्या होना चाहिए? Right, what you're saying is, KR, I have observed some event A. Given that I have observed this event A, what is the expected value of the random variable x? Right. So in other words, if I do an experiment in the morning, right, what is the expected value of the measurements that I get? Okay. Or I could say that if I'm teaching the course in fall 2019, right, conditioned on this being taught in fall 2019, what is the expected value? And conditioned on this being taught in fall 2020, what is the expected value, right? So you can condition on different events and get a mean value for that. Okay? So what do you think the definition should be here? क्या नहीं चाहिए definition? Salman?
सर सेम ही होगी, बस जो जहाँ पर x जैसे f कैपिटल X लिखा हुआ था वहाँ पर x कैपिटल X गिवन ए हो जाएगा.
Good, right? So this is the same definition, except that the PDF of that you're going to be working with is not the PDF on X, but rather the conditional PDF on X that we talked about in the previous chapter. Okay? So this is going to be the conditional PDF of X given A dx, right? So it's exactly the same idea, except that you're working with a conditional PDF instead of a normal PDF. Okay? And this is, of course, for a continuous random variable. Discrete random variable के लिए, the only thing that's going to change is that the integral is going to be replaced with a summation. Right? So this is xk, and you're going to be working with a PMF instead of a PDF. Right? And similarly, oops, I can define any expectation on any function. So expected value of g of x given A. I can define that as well, right? So I could say what is the expected value of the squared values of my measurement given that I do the experiment in the morning. Okay? And this is just simply going to be equal to g of x and f of x given A x dx. Right? And this is for a continuous random variable. You can, of course, let me write that. This is summation k g of x k probability of x given A xk. So this is for a continuous random variables. This is for a discrete random variable. Okay. So let's do an example quickly. So what you're given is that x is a Gaussian random variable, actually a standard normal random variable, right? And once again, there's a conditioning operator, in other words, which is कि जी एक बत्ती है वो जलती है, right? वो कहती है कि यार ये is it greater than 0 or is it less than 0, right? And if it turns on, that means it's greater than 0. And you're required to find the average value of this random variable given that the random variable is positive. So you have some information about the random variable. Now, somebody tells you that the random variable, the observation that I get of the random variable is positive. If it is positive, what is the value that you can expect out of this conditioned random variable? Okay. So what you're interested in finding is the expected value of x given that you know that the random variable is non-negative. Okay, this is what you're interested in finding. So how do I go about this? So I just apply the definition, right? The definition is expected value of x given x is greater than 0. This must be equal to integral minus infinity to plus infinity times x and times f of x given x is greater than 0, x dx. Okay. So who can help me here? What will this be? We've actually done this exact example in the previous chapter. So, कौन बताएगा? Maz?
सर वो ये होगा ना कि f of x divided by the probability of the event x is greater than 0.
Yeah, good. Right. So this is f x of x divided by the probability that x is greater than 0. But there's a catch here. Ghazi?
U of x.
U of x. Good. Right. So this is only when the random variable is positive, and the PDF is 0 when the random variable is negative. Okay. What is the probability that x is greater than 0, by the way, for a standard normal random variable? There's a symmetry involved, right? So what is it? 0.5. So this probability is half, right? So this turns out to be equal to yeah. So this turns out to be equal to this thing, root 2 divided by pi e raised to power minus x squared divided by 2 u of x. Okay. So you're 1 upon root 2 pi tha, but then the 2 is in the numerator, so that you get root 2 in the numerator. Okay. All right. So then what you need to do is to just compute this integral. That's it. Right. So this integral therefore goes from 0 to infinity. And this is root 2 by pi here, and this is x, and this is e raised to power minus x squared divided by 2 times dx. So anybody who can help me here in the computation? Integral किस तरह compute करें? Isha?
Sir, integration by parts.
No, not necessarily. That आप कुछ कहेंगे? जी? गाजी कुछ कह रहे थे?
Substitution.
Substitution. Right. So this is really simple. I mean, so you see, this x is actually a derivative of this. Right. X is a derivative of x squared by 2. Right. So you just use that chain rule. Right. And based on that, I can just write this as root 2 by pi, and this is e raised to power minus x squared by 2, and this is infinity and 0, and there's a minus sign here. Right, because x squared by 2 minus x squared by 2 का derivative is minus x, right? So यहाँ पे minus आएगा, right? And this is root 2 by pi. Right, so this is your answer. The average value of this standard normal random variable, given that the standard normal random variable is non-negative, is root 2 by pi. Okay? Okay. All right. And then there's some sense of total law of probability that you can work with expectations as well, right? So let's do this. Let's say you're given this information. You're given the expected value of x, where x is a lifetime of a person, right? So that's a random variable which represents a lifetime of a person. You can compute the expected value of X given that person is a smoker, right? And you're familiar with what the expected value of X is given that person is a non-smoker, right? So this is another example of conditional expectations, right? So the conditioning event is now not necessarily an event on the random variable being restricted to a certain interval as it was in the previous example, but now there's the conditioning is on some other experimental outcome, right? And that is, does that person smoke or does that person not smoke, right? And given that the person smoked, you can compute the average value, average lifetime, or a life expectancy. And given that person smokes, you can compute the average life expectancy, right? Now, if you're given the two information, the expectation of X given smoker and expectation of X given non-smoker, the question is, can you find the average lifetime within the general population, regardless of whether the person smokes or not? I mean, can you get rid of this expectation? In other words, okay, for that, something like the total of probability is applicable. Okay, so what I'm asking you to do is compute the expectation of X, right? And if I just compute the expectation of X, this is the definition, right? However, from the total of probability, I know that Fx of X is f of X given smokes, probability of smokes, plus f of X given non-smoker times X, probability of non-smoker, right? So remember, but this is from the total law of probability. Okay? If I just plug this in here, this becomes minus infinity to plus infinity, X times Fx given smokes, probability of smokes, dx, plus minus infinity to infinity, X given does not smoke, X probability of does not smoke, and dx, right? And this becomes equal to what? Who can help me here? कौन बोला? Maha? Okay, Mohsen, go ahead.
So the probability of S and probability of NS are constants, so they can come out to the integral of your expectation of X given S or X given NS.
Good, right? So this is and this is probability of smokes plus and what you have inside the brackets is nothing but the conditional expectations that we've seen above, right? Okay, so this is expected value of X given smokes times probability of smokes plus expected value of X given non-smokes times probability of not smoking. Okay, so this is this in some sense the total law of probability applied to expectations, right, or the average values. Okay. What is the assumption, however? The assumption was what? Okay, either a person is a smoker or a not smoker. In other words, those two events that we talked about, they have to be mutually exclusive and they have to be exhaustive, right? If they have to be mutually exclusive and they're exhaustive, I can extend this to a very, very general setting. In general, if if events A1, A2, AN are mutually exclusive and exhaustive, what we have is that the expected value of X is equal to summation K equals 1 to N expected value of X given A sub K times probability of AK. Okay, so this is something that we may use in some of the homework problems. Okay, any questions here? Okay, so we have 8 minutes. So I can just quickly introduce the next topic, which is probably something that you may not have done in an undergrad. इससे पहले जितनी भी चीजें, these are, I mean, probably common practice. It should be commonplace in undergraduate curriculums. Mohsen, you have a question?
So could you go back to the general formula? I wasn't done writing that.
Yeah.
Okay, sir.
ठीक है? So I'm going to upload these notes anyway, right? Okay. So transformation of random variables. And the transformation of random variables, as one of the problems that Isha stated in the very beginning, was if you have y equals g of x, right? If you know the randomness in x, can you not use this functional form to determine the randomness in y exactly as well, right? So in other words, given a PDF or a PMF on x, wouldn't this functional form also allow you to compute the PDF or PMF on y? And the answer is of course yes, right? And this section is going to deal with those, right? How can we do that? Okay, in order to derive a general relationship, right? In order to derive a general relationship, before we do that, let me just give you a toy example. And that toy example, to illustrate the general ideas involved, right? That toy example is the simplest function that you can think of, which is y equals a times capital X plus b, right? This is a simple affine function. Okay, the problem statement is that given f x of x, determine f y of y, right? This is what you want to determine. Okay, this is the problem statement. How do we go about this? The way we go about this is through starting out with CDFs. Okay, let me first of all assume that a is greater than 0, right? That means, which implies that the function is, what can I say about the function? Huzaifa, if a is greater than 0, function क्या दिखेगा?
So like in terms of the derivative of the slope of the function,
is it going to be increasing or decreasing?
It's going to be an increasing slope every time.
Right, so it's monotonically increasing. Right, so in other words, if I were to sketch this out, if I were to sketch this function out, this would be something like this. Actually, not centered at 0. Something like this, depending on what b is. Right? B is a positive and negative, by the way.
for the one that you've made, उसके अंदर तो negative है.
इसके लिए क्या है?
Graph जो आपने अभी line draw की है उसके लिए तो negative है.
B is negative, right? And A is positive, right? So this is where B is. Okay, this is B on the y-axis, and this corresponds to the case when A is greater than 0, right? This is an illustration for A is greater than 0. Okay, the key idea here is to map events, or actually, key idea in any transformation that you do is to map events on X in terms of events on Y, right? So what I mean by that is, let's try to look at the event capital Y is less than or equal to small y for any value small y, right? So this is an event. When the random variable capital Y is less than or equal to small y, that's an event, right? Can I map this event to an event on X, right? So let's say ये small y था, right? So what is that event on X? So I say that this is equivalent to an event, right? Which is what? Which is, because this is a monotonically increasing function, capital Y is less than or equal to small y if and only if capital X is less than small x, right? Where small x is what? Small x, the value on the x-axis that you get, or the intercept on the x-axis that you get when capital Y equals small y. Okay, it's a solution to this equation. Take a solution to the function, okay, or the root of the function, right? So the event that capital Y is less than or equal to small y is exactly the same as this event, right? Because capital Y equals ax plus b, okay, and this is the same as the event that x is less than y minus b upon a. Okay. Achha, let me introduce a step here to make one point clearer. So this is the same event as ax is less than y minus b. No problems here whatsoever. Okay. And I say, okay, this is the same event as x is less than y minus b upon a. And I claim that in going from here to here, I have to be careful, right? And in going from here to here, actually, I've used the fact that a is greater than 0, because had a not been greater than 0, this would not have been a correct implication, okay, or correct conclusion, right? Because a then would have been a negative number, and if I divide with the negative number of both sides, the equality sign changes. Okay? But since a is positive, if I divide by a positive number on both sides, that's fine. Okay? The equality does not change. Okay? And graphically, I can see this here as well. And the graphically is capital Y is less than small y is this event, right? Which is equivalent to this event. Okay? For each one of those points on the y-axis here, I can find a point on the x-axis here, and there's a one-on-one correspondence between the two. Okay? So my conclusion, which is an important conclusion here, is that this event is exactly the same event as this here. Okay, so it's a mapping of intervals, if you will. Okay. Now this is enough for you to determine what the PDF is. How so? I start out with the probabilities. Let me start out with the probability that capital Y is less than or equal to small y, right? Which, remember, is nothing but f, capital F, y, y, right? The CDF. And this is the probability that x is less than y minus b upon a, right? Which is nothing but the CDF of x evaluated where y minus b upon a, right? So fy of y is equal to fx of y minus b upon a. Now, how do I go from here to the PDFs? क्यों मोहसिन? PDFs पे कैसे जाऊं? Mohsin, can Huzaifa?
Sir, I
Achha,
can
so
hear
go
you.
ahead, Mohsin, please.
Sir, I've forgotten whether it was derivation or integration. I'm
Okay,
guessing it was.
Yeah, so one of those two. So it's differentiation with respect to y on both sides, right? So I get capital, so fy of y, which is actually the derivative. This is d by dy fx y minus b upon a. What will this be equal to? I just use the chain rule of differentiation. So this is times d by dy of what? Y minus b upon a. And therefore, I get a very, very nice, elegant solution to this. This is just simply equal to 1 upon a times fx of x, fx of y, sorry, minus b upon a. Right? So this is an elegant result for a very simple problem. And then in the next class, what we're going to try to do is we're going to try to generalize this to any function, right? And that might take some amount of effort, but we'll get there. Okay. All right. Any questions?